So good morning. Greetings from Chandler, Arizona. Uh, really glad to be able to have this opportunity to talk about SPDK today. I think as Vladimir went through, we've got a good agenda. Wish we could be doing this in person, but this will have to do. I think you're going to get a lot out of today's session and then the next 2 days as we talk about PMDK and the Intel VTune profiler. So let's talk a little bit about my agenda for today. So we're going to cover 3 main topics. First, the state of the community. We love talking about the technology and all the performance that SPDK provides, but this is it's a community. This is a project that Intel started, but there are a ton of companies that are investing in SPDK, and I want to take some time to kind of call that out and list some of the major milestones we've achieved in that area over the last year. Then, of course, I'll go through the technology, where are we at from a technology perspective, what are some of the key features that we've added over the last year, and then just give a little bit of perspective on the future. Where are some of the major areas that I think SPDK is going to be moving over the next maybe 12 to 18 months? Okay, so let's start by looking at the community. So just want to provide a little bit of background for those maybe that aren't familiar with SPDK, kind of how it started. This started as an internal project at Intel 7 years ago, which is kind of crazy to think back on. I joked last year when we started this project at Intel, it was nicknamed, it was codenamed Waikiki Beach, and I joked that maybe instead of having our summit in San Jose, we could have it in Waikiki Beach, this year. That didn't happen. I think we actually took a step backwards, but maybe we'll be able to do that again sometime in the future. About 5 years ago is when we started open sourcing SPDK, and that started with the SPDK NVMe driver. And so we started open sourcing that on GitHub, and then over time we started open sourcing all of the components in SPDK. Today, everything that SPDK is doing, it's all open source from day one. So all the patches are out on our Garrett instance, so you can always review what the latest work that's happening in the community. In 2016, SPDK released our first NVMe-over-Fabrics target for the RDMA protocol. That was a big step. There wasn't an open source BSD licensed user space target available yet, and so SPDK was first in that regard. The following year, we had our first SPDK summit in the US, so that was 3 years ago. And since then, we have at least one, if not 2 of these summits every year, typically one in the US and one in China. And then later in 2017, when the project first started, the core maintainers were all from Intel, but in late 2017, we added Shuhei Matsumoto, who's a software architect from Hitachi. We added him as a core maintainer, and I'm going to talk in a little bit about other core maintainers that we've added even more recently. And then late 2018, this was a really big step as the NVMe specification for NVMe TCP was being developed. SPDK was working in conjunction with all the spec work so that when the spec was released, we had a user space implementation of not just a target, but actually the host driver as well. And so this is something that we're continuing to do within the community, is to track closely with what's happening in NVMe and be ready to enable the key features that it's enabling. So we look at recent community milestones. So this is really, what are the major things that have happened since we had our last summit in the spring last year in San Jose? We've added 2 new core maintainers, Alexei Marchuk from Mellanox. He's been very involved in the SPDK community with a specific focus on NVMe-over-Fabrics, both TCP and RDMA, both the target side and the host side, and has been a really key reviewer to make sure we keep the quality of the work going into SPDK very high. And then Tomek Zavodsky, who's been involved with SPDK for several years, he's really been driving our release process. As SPDK has grown, it's become even more important for us to just make sure that our releases are on time, high quality, meeting all of the different types of reviews and things that we want to make sure are done before the releases are made. Tomek's been huge in making that happen, and he's also been a big contributor in a lot of technical areas, especially SPDK logical volumes. I'll talk a little bit more about that in a couple of slides. We had another summit in Beijing back in September, very well attended. We had over 300 attendees over 2 days. This was an SPDK, PMDK, and Intel VTune summit that was there in Beijing. Hope that we can do that again sometime soon once we have COVID behind us. We also have developer meetups, which are different than these summits or virtual forums. So where these summits and virtual forums are primarily presentations that key contributors are making to a wider audience, the developer meetups are much smaller, much more intimate, where the architects and developers are getting together on whiteboards and just working out major architectural and design things that are just best talked about when you can get everybody into a room. These are really productive sessions, and we had one of these at Nutanix back in November and had, I think, 12 to 15 developers there, and we were able to work through a lot of issues, talk about a lot of topics. It was a very productive couple of days. And then with SPDK, Intel has had a continuous integration CI environment for a long time, for several years. It's been public. But what we've wanted to do over time is SPDK grows. There's a wider variety of hardware that we want to expose the SPDK code base to. And in a lot of cases, things that Intel either can't or isn't best equipped to be able to test. And so both Mellanox and Broadcom have brought their own CIs online and hooked into what we have on SPDK.io so that they can test things like latest Mellanox NICs, test on different architectures, test fiber channel. And so we've just really been able to expand that and be able to get broader coverage and to be able to extend our CI environment to be able to have more companies be able to plug into it. And then we had our first LTS release. So Tomek was huge in driving this. There have been a lot of requests in the past to have more of a long-term stable release for SPDK. Typically in the past, we've backported patches one release, so back one quarter. What we're going to be doing now is the 20.01 release that was in January. We're going to be maintaining that for a full year. And so we've already done, I think, 2 point releases on that. We'll continue to do those over the next 2 to 3 quarters. And so our plan is that we will continue to do that on a yearly basis with the January release. So when we look from a community perspective on what's being committed to the SPDK repository, so each of the rows here corresponds to about 1 year in time. So just based on how release dates and stuff have changed over time when we do releases, it's not perfect, but this is a pretty good overall. You can see in the last year, our total patch count, we hit almost 4,000 patches, so up about 30 to 35% over the previous year. You can see the total number of committers we had did go down a little bit, but if you look at that last column, it's looking at the patches from the top 10 committers. So, with any project, you have, a certain number of committers that are just very, very prolific, and what you can see here is that the number of patches coming from those top 10 committers is actually continuing to go down. And what that means is we're getting more and more of these committers to be more and more active. So overall, these 85 committers we've had over the last year have been much more active. We're just seeing a lot more variety in the type of work that's getting pushed up into SPDK from a wide variety of people. And then when we look at the GitHub visitors. So we kind of use this just as a metric of who's going out and looking at our webpage. We don't have any idea of who exactly those people are. All we can get is a count. But it just shows that over the last year, we've had over a 25% increase on the number of unique visitors to our GitHub page. And so this is people who are either searching for SPDK on GitHub, looking at our documentation on GitHub, going and looking at, reviewing or submitting issues. And so it just gives us a little bit of perspective that this community is, continuing to grow just based on who's out looking at it on GitHub. Okay, so that's a little bit of a snapshot on where the community's at. Let's talk a little bit about the technology. What have we added in SPDK over the last year? So of course, SPDK, it's not SPDK without the performance. And so performance is always, really at the foremost of what we're doing. That's why people are excited about the work that's happening in this community. And we've done a lot of work in this area over the last year. Ben Walker and myself did quite a bit of work last summer to continue to drive the efficiency of the SPDK NVMe driver to the point where now we were able to demonstrate over 10 million IOPS on a single Xeon CPU core. Ben gave a fantastic talk on the details on this at SNIA SDC last summer. If you want to get more details, listen to his talk. It's really good. You can also go out to the SPDK blog, spdk.io/blog, and there's a really extensive blog post that talks more about the work that we did there to enable that. And so as we did that, that allowed us to start, then focusing on other parts of the stack. Where can we continue to make other parts of SPDK more efficient? The NVMe driver is great, but the NVMe driver is only one part of a broader application. And so we've spent a lot of time looking at the NVMe fabrics target, especially for TCP, and how we can make that more efficient. Ben and Seth are going to talk a lot more in detail about this, so I'm not going to go into details on how we did this. But some high-level numbers are, we're now able to hit 3.5 million IOPS on 8 Intel Xeon CPU cores. We thought we had a pretty good performance story on this last year, but this number is 87% higher than what it was even 9 months ago. So it's getting to the point where we're starting to approach NVMe RDMA-like efficiency on TCP, at least for when the target is transmitting data. And Ben and Seth are going to go into a lot more detail on that. And then you can even just see, just for large sequential reads, we are more than saturating. We're saturating about 150 gigabit of Ethernet using just a single Xeon CPU core. So please stay on for Ben and Seth's talk to hear more about how SPDK has been able to achieve that. And then, of course, there's a lot of other, other things across the stack that we've done from a performance perspective over the last year. One I'd especially like to call out is on the logical volume front. Tomek Zavadski's done quite a bit of work here, implemented a new metadata layout to significantly improve how we allocate clusters for doing writes on thin provision volumes. We've seen some huge improvements on that. We're working on getting some benchmark data, but it looks like that's going to be on the order of 2 to 3x more efficient for doing those writes. And then just continuing to do other I/O path optimizations, looking at just little things we can optimize here and there, where we've gotten up to 10% better performance per core, top to bottom for the stack, when we're doing things like logical volumes on top of NVMe SSDs and then presenting those over an NVMe over fabrics. Intel DSA. So DSA stands for Data Streaming Accelerator. The driver the driver acronym we use for this is IDXD. SPDK chose to use the same acronym that's being used in the Linux kernel. It's a little bit of a mouthful. It's a 4-letter acronym instead of 3. But this is a feature that's going to be available in future Intel processors. It effectively replaces Intel Quick Data technology. So for people that know, have heard of Crystal Beach DMA or IOAT, that's what Intel Quick Data technology is. DSA is going to be a even higher performing, we call data streaming accelerator, data movement engine. It has a lot more features than that. So Paul Luce has been driving the work on this. Been using some simulators we have available in Intel to make sure that this is available to be used in SPDK once these processors do become publicly available. And so he's done work to take the copy engine framework that we used to have that just did data copies and data fills. And so we're moving that because now we're going to be extending it to support more of the features that DSA provides. So this new framework has APIs for copy and fill today. But the next release, I think a lot of this work has actually already been merged, and you can get it on master. It'll be part of the 20.07 release. It'll be next month, but it's going to add also APIs for doing comparison of two buffers, doing dual cast. So for example, being able to copy data maybe to another host buffer locally, but then also a remote buffer, maybe over a non-transparent bridge link. And then DSA also supports CRC and diff-dix, and so there's APIs for that as well. And so this acceleration framework works like a lot of the other frameworks that we try to do within SPDK, where it will offload to Intel DSA if it's available. If not, it will use the CPU. And when I say CPU, it'll use ISA-L, which is the optimized assembly libraries that Intel develops to basically be able to do a lot of these operations as efficiently as possible using the latest and greatest instructions that are available on those processors. And so that's just the framework, but we will also be working on integrating some of these features into our NVMe-over-Fabrics drivers and targets, and also the iSCSI target later this year. So for example, a lot of cases you have things like doing CRC checksums on on digests or on payloads, and so we're going to be working to make those asynchronous, and then being able to offload those and further even make that more efficient when those types of CRC checks are enabled. Okay, just going to do a quick time check here. Next, SPDK top. So again, John Kariuki is going to be doing a demo on this just after my talk, so I'm going to just touch on this briefly, let him go into the details. But this is a utility that Maciek Szwed from our team in Gdańsk, Poland developed, and when you think of top, it's classic Linux utility, lets you know what the processes are doing on your system, how the cores are being utilized. When you're doing pulled mode software like SPDK, top's not real effective. It's just going to tell you 100% of the CPU is being used. And so what we wanted to provide was a utility to show on those cores what's actually the work that's being done. So what we've been doing is going into the pollers that we have in SPDK and instrumenting them to indicate whether they did real work or whether they just checked for work but didn't really do anything. And so what that gives us is data to know when these pollers are busy or idle, and we can aggregate those stats to then know on a per SPDK thread basis or a core basis how busy or how idle were those. And the reason we want to do that is because, and I'm going to talk more about this when we look forward, what we're going to be doing over the next 12 months is being able to enable development and debugging and analysis for being able to schedule SPDK threads between cores. So what we want to be able to do is take threads off of one core, put them on another core so that we can shut some cores down to be able to save on power. And then even taking that further is being able to modulate the CPU frequency using features like Intel Speed Select technology. And so SPDK top is, in the short term, going to be able to give us a lot of really good tools for developing and even debugging some of these features as we add them. But then longer term, once those features are in place, is be able to use SPDK top as an analysis tool to understand more deeply about how your SPDK application is operating. Okay, pluggable transports. So NVMe and SPDK for a long time has supported multiple transports, both in the host driver and the target libraries. But one of the things Seth Howell's been working on over the last several months is to make this easier to add new ones. So before there was a lot of busy work as far as like getting these transports integrated, getting new ones online, and also even being able to potentially add out of tree ones. So Tomek and Paul are going to be talking more about this on we're kind of looking at NVMe-over-Fabrics. The target is not just an NVMe-over-Fabrics target, but really NVMe emulation. And this NVMe-over-Fabrics pluggable transports is really setting the groundwork to use it more as this type of NVMe emulation framework. And so you can see from an NVMe driver perspective, we've always supported, PCIe transport, obviously. We've added RDMA, also TCP. The NVMe target, so Broadcom, Anil from Broadcom added the fiber channel transport for the NVMe target last year in our July release. And as I mentioned, now out-of-tree custom transports are also supported. So if you're looking for something that can do NVMe emulation, look at SPDK. The framework that we've put together is really setting it up well to be able to do things like that. and I'll talk a little bit more about some of the other, I say, fabrics transports that are on the way, and you're going to hear Tomek and Paul talk more about that as well. So looking at NVMe character devices. So SPDK has always provided a framework and utilities for being able to manage SSDs that are controlled by the SPDK NVMe driver. So we have tools like NVMe Identify. We've added JSON RPC interfaces to be able to send like custom commands to SSDs, things like pass-through commands like you could do with the Linux kernel. But one of the requests that came up, something that Nutanix was looking at, and we talked about this quite a bit at the developer meetup last year, was being able to, can we use existing Linux utilities like NVMe CLI to be able to manage these SPDK-owned SSDs? And so what we added was something called Linux, the NVMe character devices using something called Linux queues. This is character device and user space. And so for those that aren't familiar, what this allows you to do is to, from user space, be able to register a character device that will show up in your DevFS. But when a process performs operations on it, your user space process will receive notification and can handle those. So instead of them being handled in the kernel, they're actually handled in user space. And so what we're able to do is basically have SPDK present character devices that look like dev NVMe devices. And so what this allows us to do is use standard Linux utilities with SPDK, things like NVMe CLI for doing all the different types of management commands that it provides. And NVMe CLI, Keith Bush is the maintainer on there, and he's constantly adding new features. And so we want to be able to take advantage of that, right? Like, it's great to be able to leverage what the broader open source community is doing. Of course, there's still going to be a place for some of these more custom SPDK utilities, but being able to leverage what's out there is great. And that works really well for people that are maybe migrating from using the Linux kernel driver to using SPDK. And then also smart control. So for being able to monitor the health of the SSD, so smart control also works with this queues interface that we've added for SPDK. And then finally here, Intel VMD. VMD stands for Volume Management Device. This is a feature that's available on root ports of Intel Xeon scalable processors. And it provides a couple of different features. One is SSD hot swap reliability. So open source, Linux kernel especially, has made huge improvements on doing hot swap. In fact, the Linux kernel, it's pretty stable, but a lot of times you actually run into issues at a platform level, like at a BIOS level, where it's limited what the Linux kernel can actually do. And so what VMD does is it provides the ability to sort of hide those SSDs from the platform itself. You install a VMD driver to do all the management of the PCI devices underneath of it. And then it also provides you a way to do LED management for those direct attached SSDs. And so the Linux kernel has provided a VMD driver for a long time, and in cases where you do not have an IOMMU enabled, SPDK will just work with SSDs behind the Linux kernel VMD driver. But for cases where you do want to use the IOMMU, the SPDK community has added a native user space SPDK VMD driver. This was added in our release last July. And so what this allows you to do is to bind the VMD endpoint to the SPDK VMD driver. And then this VMD driver and SPDK will actually do all the enumeration of the devices behind it. It will monitor for hot plug events. You'll be able to do LED management, etc. Okay, so that's on the technology. Looking back, now let's take a look at forward. What are some of the things we're going to be looking at over the next year or so? So NVMe over fabrics without the fabrics. Tomek and Paul are going to go into a lot more on this, but at a high level, this target has gradually evolved over time. I mentioned, I guess 4 years ago was when we did the first release with just RDMA. Now we've added TCP, we've added fiber channel. What's happened is that the architecture has very clearly come down to where you have common code for general NVMe target functionality, And then you have these pluggable transports for how do you expose it over RDMA, how do you expose it over TCP, over fiber channel, etc. But what we're seeing now is actually, now that we have this emulation framework, we have these pluggable transports, we're finding a lot more really neat use cases for leveraging all this work we've done in the Fabrics target over these last few years. And so one of the big ones is virtualization. This is an area that Intel, Nutanix, Red Hat are collaborating on, called Muser, mediated user. Tomek and Paul will be talking more about that. And then they're also going to be talking about the SmartNIC use case. So when you think about a SmartNIC, typically this is an accelerator device, typically attached over PCIe, where again the host sees NVMe devices, but the NVMe is actually being emulated by that SmartNIC device. And so, yeah, Tomek and Paul will talk a little bit more about what that's going to look like and what SPDK is going to be doing to help enable that. So next is computational storage. And so, computational storage, this concept has been talked about for years. There's a SNIA technical working group that's been working on this. I actually tried to look for a picture that really described this really well, and I had a hard time finding one picture that could really do it. So I'm going to do my best to describe it using words, but I think a lot of people are already familiar with this. It's trying to move the compute closer to where the storage is. So instead of having to transfer all the data and then process it over here, can we actually move the compute closer to where the storage is? And this paradigm has been around for a long time. MapReduce, other things where we're doing this. But we're looking at how do we do this maybe with something like NVMe? Is something like that possible? And so when we look at that compute, that typically comes in two different forms. One is what we would call fixed function. So for example, compression. Can we send the data but then have the device or the target actually compress it, or actually do the decompression when it reads it back? Things like hashing, things like erasure coding. So these are things that are fixed function. They're very well defined, typically even by a standard, or an algorithm that's very well known. But then also programmable functions. So, having the ability to maybe like a, kind of needle in the haystack type problem. You have a bunch of data and you're looking for specific, maybe, rows in a database table. And so being able to describe those types of operations from a programmable perspective. And so, this is an area that I really anticipate standardization efforts to be, moving forward over the next year. I think there's a ton of interest in this across the industry, and I think you can definitely expect SPDK to be at the middle of that. So I think whatever happens, if there's standardization that moves forward within NVMe, you can definitely expect SPDK to be in the middle of that from a number of perspectives. Then power efficiency. So I talked a little bit about this when I was going over SPDK top, but we're going to be doing a lot more work on these SPDK thread schedulers. We've been doing a lot of work over the last year to really separate out. We've always had this concept in SPDK where you have one thread per core. And from a POSIX thread perspective, we still have that. You have one POSIX thread per core, but we have an SPDK thread abstraction now, which basically is a set of pollers and timers. And these SPDK threads, you can move between cores now. And so now that we've separated those out, and we have these heuristics to be able to count, how busy are they or how idle are they, we can move the threads between the cores. And we want this to be dynamic, right? This can't be an administrator option. It has to be something where the application is automatically detecting when things are idle and moving threads to another core so we can shut a core down. When the I/O workload comes back up, to do the reverse process, move threads to idle cores and spin those cores back up so they can start doing work. And then also enabling Intel Speed Select technology. So Intel is continuing to improve the ability of being able to do speed select. So, decreasing the amount of time that it takes to change frequencies. A lot of features like that we're going to, be enabling within SPDK so that, let's say that you have a very idle system and you get all of your SPDK threads moved to a single core. On that single core, can we continue to reduce the power consumption by reducing the frequency? And so I think these two together, between moving threads between cores and then also being able to modulate the frequency, is going to give us a lot of really powerful options for SPDK to really get some of those, that benefit back. That's always one of the drawbacks to doing a pulled mode system, is that you're always using CPUs at 100%. And this is going to be a major focus for SPDK to really be able to significantly decrease that power consumption to really make an efficient SPDK application, not just from a performance perspective, but from a power perspective as well. And then we're also actually going to be working on interrupt and blocking mode support. So Xiaodong Liu from our team in Shanghai presented on a little bit of this in one of our community meetings last month, where there's some use cases where you want to use SPDK because you want to have your code all running up in user space, but you don't have the high performance requirements. So for example, maybe you are you want to have an SPDK process that is invoked in conjunction with each container on a system. So you have many more containers than you have cores on your system. So you can't have a pulled mode thread per container. And so in that case, pulled mode's not possible, but being able to take an SPDK application and being able to have those pollers block on like a file descriptor or on an interrupt. And so we're going to be continuing to work on that to provide the ability to run SPDK in this type of blocking mode model, where you're not going for the performance. This isn't a performance play, but it allows you to still be able to utilize SPDK and all the features it is providing for some of those more limited use cases. So that brings me to the end of our State of the Future. So call to action. Yeah, please stay on for the demos and the other talks today, and then also tomorrow and on Thursday. So, I know a lot of people from the PMDK and the Intel VTune teams. You can expect to get a lot of good information from their talks as well. Keep up to date on what's happening with SPDK. So I mentioned our blog. We have fairly regular blog posts on our releases or on cool new things we're doing, like the 10 million IOPS on a single Xeon core. We also have regular performance reports. So Karl Latetsky and John Kariuki is also very involved with benchmarking SPDK every release. And so if you go out to the SPDK.io website, you can get those performance reports. They are very, very extensive. Really encourage you, if you want to know more details, if you want to get additional numbers on top of what I've talked about today, or what like Ben and Seth are going to talk about around NVMe TCP, there are some great NVMe TCP performance reports on our website. Please go check those out. And then just jump in. Certainly today, if you have questions, please use the Q&A to ask those questions. But really, at any time, we have a Slack channel. If you go to spdk.io to our developer site development page, you can get the link to our Slack channel. We always have people that are on there. The great thing about SPDK is we are truly global. We have people in Europe, Asia, the US, and so if you've got questions, there's always people that are on there that are available and willing to help answer your questions. We have our mailing list and our community meetings. So we have community meetings twice a week, one at a time that's more Euro-friendly, one at a time that's more Asia-friendly. These are other great opportunities to come in, hear more about what SPDK is doing, or even come and talk about what you're doing. We've had people come in and talk a little bit about their use cases, maybe some bugs that they're reporting, and why they're running a use case a certain way. It's really a great way to get more involved. So with that, I am going to turn it back over to Vladimir for any questions.
Thank you, Jim. Yeah, we have a couple of questions from the audience. Just a quick reminder, as Jim mentioned, use the Q&A panel to ask questions at any time. We'll answer them at the end of each talk. Even now, if you have a question for Jim, first enable the Q&A panel at the bottom of your WebEx window by clicking on the question mark, and then type the question there on the right. Jim, we have two questions for you. First, are you planning to add quick transport to SPDK in the future?
Quick transport, that's a great question. Yeah, so for those that aren't familiar with Quick, so Quick is it's a transport that Google came up with. It's becoming more standardized, and it's a reliable transport like TCP, except that it actually runs over UDP, and so it has a lot more potential efficiency. So when it comes to QUIC, it's definitely an area that the SPDK community is looking at. As with anything, NVMe over QUIC it's a really interesting possibility. But from a standardization perspective, it's not there yet. And so I think over the next year, I think you can expect more people to be looking at it. Certainly if from an NVMe standards perspective, people start looking at how to do NVMe over QUIC, SPDK is certainly going to be in the middle of that and looking to provide that support within our upstream code base.
Thank you, Jim. Second question, is there an VMD for Windows or Mac OS?
Is there VMD for Windows and Mac OS? So Mac OS, I'm not sure about. I don't believe so. I do know that there are VMD enabled drivers for Windows. I'm not the expert on those, but certainly if you find me offline, you can send an email to james.r.harris@intel.com. I'd be happy to point you in the direction of somebody who might be able to better answer that question.
Thank you, Jim. One more question just came in. Will the new Excel API and DSA replace DPDK drivers in the future?
Oh, that's a great question. Really good question. Yeah, so for those that aren't familiar, Paul's done some talks on this in the past on how SPDK uses the DPDK framework for crypto and compression offload. And we spent a lot of time, looking at, DPDK framework, the Excel API, and what we've decided is that one of the reasons we like the DPDK framework is because the quick assist drivers are far, far more complex than the Intel Quick Data, like the CBDMA, or even the new DSA driver that Paul's been developing. And so we really don't want to redo all the quick assist work that DPDK is already doing. And so we're really planning for compression and crypto, especially to continue utilizing the DPDK framework for those. But for the simpler offloads, especially ones that are driven by simpler hardware interfaces like Intel Quick Data and DSA, that we will use the Excel APIs for those. So that's kind of the current state. Of course, things could always change, but that's kind of where we see things fitting today.
Perfect. One more question. Any work and testing done on ARM platform?
Yes, so there is. So Mellanox is the Mellanox CI is testing on ARM platforms. There are developers from both Mellanox and ARM that are active in the SPDK community and are pushing patches. So yes, there is work continuing to be done to enable SPDK on ARM.
Thank you, Jim. One more. Any update on C-Star integration?
C-Star integration, yeah. So C-Star is another pulled mode framework developed by ScyllaDB. There's a lot of similarities between SPDK and C-Star. C-Star has a user space TCP stack. In fact, they have a user space TCP stack that works on top of a DPDK pulled mode driver so that the entire TCP stack runs in user space. I did some prototyping last year to take a look at what would it take to integrate that with SPDK, and made some progress. I think it's definitely something that is possible. The native DPDK part of it within C-Star isn't being really actively used. Some of the newer pulled mode drivers within DPDK had a hard time getting working. One of the other things that we started to find, though, was that with the new interfaces that we're seeing in the Linux kernel that we're utilizing, that Ben and Seth are going to talk about here in a minute, we were starting to see huge improvements on our use of the kernel TCP stack. And so Right now, we've put the C-Star integration stuff on hold. Just based on the improvements we're seeing on the kernel TCP side, we're just deciding to focus our energy that way, just because the kernel TCP stack is so well maintained. There's so many people that are really hammering on it, that on the C-Star TCP side, we think there's some potential there, but it's not as actively maintained and supported. And so there's a lot more work we would need to do there. And so it's something we'll continue to keep an eye on. But I think right now the improvements that we're seeing on using the POSIX kernel TCP stack are it's really promising, and we feel like that's probably the better way for SPDK to move forward.